Greetings to everyone. My name is Chetan Chauhan. Today we are going to have the red wine quality analysis use case where we are going to cover the data transformation, model filtering, and the prediction. Focuses on the detailed assessment of the red wine quality based on the data sets provided. Our objective is to find out and analyze the red wine quality, leveraging the statistics models. This includes the understanding of the data distribution, applying the transformations on the top of it, and predicting the quality based on the various features been provided. Talking about the data distribution, the data set for the red wine is coming from the North Portugal country. This data set includes 1599 observations, and there are 6 key variables related to the wine quality. We have took the subset of 400 observations for the detailed analysis and the modeling. This data set includes the 5 variables or the features, I would say: citric acid, chlorides, total sulfur dioxide, pH, alcohol, and the quality, which scores between 0 to 10. This is the smaller data preview which we have it for this different variables what we see. Just to understand the data better, we have used the scatter plots and the histograms to visually assess the relationships between the variables and the distributions. This will help understand the data landscape better. Before we go to the graphs, I just wanted to say some of the insights from the visualizations. What we have found out: alcohol content is the most significant predictor of the quality, with strong and the clear relationships. Citric acid and the chloride execute the wicked trends but still hold explanatory power. Total sulfur dioxide and pH require the further analysis for the better interpretations. And ultimately, we have used the data transformations, log and the square root, which will help mitigate the skewness and improve the model fitting potential. We'll quickly go through the data distributions plots, what we have it as part of the scatter plot and the histogram. This is for the citric acid, chlorides, total sulfur dioxide, pH value, and then ultimately the quality Y. And you see the distribution for different variables, what we have it. I'll quickly jump on to the different observations, what we have it based on the graphic. From a scatter plotter perspective, citric acid shows the positive correlationship and shows slightly associated with the higher quality ratings. There is a significant variability indicating the other factors contribute to the quality. Coming back to the chlorides, there is a negative wick trend which we have seen. That's suggesting that the higher chloride levels might reduce the quality. Points are widely scattered, indicating the low predictive strength. Going to the total sulfur dioxide, there's no clear line trend is evident. Points are disparate that this could be, due to the weak or negligible direct influence. Talking about the pH, data points indicates the possible non-linearity relationship with the quality, and the mid-range pH levels favoring the better quality of it. We could still look at, when we would do the transformation around to that. Coming back to the alcohol, and this is the interesting one where we see the clear positive correlationship and making a alcohol a stronger predictor of the quality here. That's what we have got it earlier as well, based on the insights. So the higher alcohol content often corresponds to the higher quality ratings. Now I'll go back to the histogram summary. What we see for the different variables: citric acid, we see a normal skewed distribution with most values concentrated in the lower ranges. There are few instances of the higher citric acid values as well. From a chlorides perspective, there's a strong positive Q. There most of the data points are in the lower range and the few high chloride values as well. For total sulfur dioxide, there's a right skewed distributions, and majority of the wines contain the lower sulfur dioxide levels with a gradual taper towards the higher levels. pH, what you have seen, that's a normal fair distributions and centered around the typical pH level for the wine, and slight skewness which we have observed here. In alcohol, similarly, there is a slight right skew with most value concentrated around the average alcohol content. There are some outliers in the higher ranges as well, what we have seen. From quality perspective, it's uniformly distributed across the ranges of the wide quality ranges ratings. This is indicates the diverse quality levels in the data set. Going to the next slide. The data transformation, what we have it. So the data transformations were applied based on the skewness, including the log transformations and the z-score standardizations. This also ensured the consistent scaling, and we optimized the data set for the accurate model fitting. There were negative values which were also addressed to maintain the data integrity. Transformation results, what we see. Uh, This table shows the distributions of all the key variables in the data sets and transformations applied to improve the normality of it. Uh, this approach will help us out, ultimately optimizing the model fitting. Skewness calculations, as I mentioned earlier, which we have used to make the choice of the transformation with the log, square root, or anything else. And then we have applied the z-score standardization and min-max normalization for consistent scaling. So if you see in the citric acid, it is near normal. We have not applied any transformation. Chlorides, it's a highly skewed. We have applied the log transformation on top of it. Total sulfur dioxide, it is moderately skewed. We did apply moderate log transformation on top of it. pH is also near normal. We did not apply any transformation on top of it. Alcohol and the quality, there were a slightly or mild skewing, and we did apply log transformation on top of it. Going to the next slide. But the model fitting, what we have seen it ultimately, there's an overall summary. So if you see the different reasons for different model which we have applied, WEM model, power with 0.5, power mean with the 2, and then ordered weight average as well. Ultimately, what we see based on the understanding of the different model which we have applied on the data sets, the weighted arithmetic mean model, which has demonstrated the higher accuracy and with the lowest RMSE and the average absolute error. This is making it most reliable for the prediction based on the data sets and based on the transformations we applied. There's a stronger correlation as well, achieved with the highest Pearson correlation coefficient and the strong Spearman correlation coefficient as well. This is indicating the robust predictive power and line with the actual data trends. There's a consistency across matrices, like, if you compare with the other models, WAM has consistently outperformed in the error minimizations and the correlation strength. This showcasing its capabilities to generalize well on the data sets. There's a versatility also, which we have seen between the relationship for the input variables and the target variable. This is making it suitable for predicting the wine quality with the available data sets and the transform data set what we have it. So ultimately, it's an optimal choice based on the statistical performance and the low error margins. WAM is the best fitting model. It's providing the reliable predictions and meaningful insights into the data set. Going to the next slide. Variable importance. And this is very much important. Like, if we have, like, we have broken into the quality test and then ultimately the importance of the acidity, what we will discuss in this slide specifically. So what we have observed is the alcohol content is the most crucial variable impacting the wine quality and highlighting its importance in the production process as well. From a test perspective, chlorides play a vital role. It's impacting the perceived quality, which is lesser compared to alcohol and pH. Quality contribution, citric acid also shows the minimal association with the wine quality. It's indicating its lower relevance as well. And then on this acidity perspective, pH levels influence the overall test balance, which is a significant factor in the quality assessment. So this is all assessment around the variable, and it's important for the wine quality. Finally, the prediction and the validation. Using the WAB model, a test input predicted a quality score of 5, which is aligned with the expected values for the similar wines. This demonstrates the model's predictive accuracy and practical applicability in the assessing the wine quality. And there is a reason that, it's also the consistent with the domain expectations and value, predicted value aligns well with the expected quality for the similar inputs in the data sets as well. And the input values which we have used for the citric acid number one, chloride acid 0.75, total sulfur dioxide 40, pH is 3.53, and alcohol 8.3. Ultimately predicted quality what we are getting is 5 as a rounded value. This analysis underscored the importance of the optimizing the alcohol content and maintaining the balanced pH levels to ensure the wine quality. So there's an implication which we have discussed. This finding is also emphasizing the significance of the alcohol content and pH level as well, enhancing the wine quality. And pH is also you need to have it balanced, which is suggesting the ultimately focused improvement in these two areas to have a better wine quality. Limitations of the study, even though it is useful insight, study has limitations. We assume as in we have assumed the linear relationship post transformation and neglecting potential variable interactions which could affect the outcomes. What we really understand, for having the best quality of the wines is optimal alcohol level around 11 to 12% and balanced pH values around between 3.3 to 3.6 is going to give you the better wine quality.